Okay, so the last thing we want to cover is something called Bayes' theorem, and we can look that up. And here's one expression of it right here. So here it is this is I think from Wikipedia, and this is one expression of Bayes' theorem. So what does it say? It says the probability of A given B, and then it gives a expression for that. Now this is not the definition of what we mean by the probability of A given B. If we go back to our book and we check the definition, it looks like this. So this is not the same. Let's just check that. So comparing Bayes' theorem and the definition is the probability of A given B is this. And that's not the same thing as here. So we have to do a little bit of algebra to get this expression. And we'll do that algebra, but let's just see what it says here. What's that? Let me just give you sort of a simple way to think about it. And that is, here we have something like the probability of A given B, and here we are able to switch that. Now, you might wonder, well, what's the point of that? Well, we can find examples where it would be much easier to, instead of doing A given B, to be able to switch. So Bayes' theorem, that's the way I think about it anyway, is that it lets you switch the order of these things if you want. Of course, you don't have to switch the order. You don't have to use Bayes' theorem, but it gives you the option to switch. Now, you have to do a little bit more work when you switch. So you have to figure out this term, and you have to figure out this term as well, but at least you get to switch. So an example of that, what might be this. So suppose we have a box with, let's say, what do we have? 5 green and 3 blue balls. So suppose we draw one ball, look at its color, and then we draw a second ball. And we're not going to return the first ball to the box after we check it. So we might ask a question like this. What is the probability of getting a blue ball on the second draw, given that the first ball drawn was also blue? So let's just write that as two different events. So let's call B1 that we got a blue on the first ball, and event B2 is that we get a blue on the second ball. So here's a probability question, and it has the word given in it. So that means it's a conditional probability question. And we'll use these two symbols, and we can write this question like this. Given that we got a blue on the first, what's the probability that we got a blue on the second? So this is a very easy problem to answer. So given that we got a blue on the first means that I should select one of the blue balls and take it out. So okay, I'll take it out. Okay, so now we got a blue on the first, we took it out. Now what's the probability that we get blue on the second? Well, we see there are 5 green and 2 blue, so it's 2 out of 7. There's 7 balls altogether, so it's 2 out of 7. So the answer is just 2/7. So the answer is just 2/7, right? That's once we take the blue out, now what's the probability that we get a blue again? Just 2 out of the 7 here. Okay, so that's very easy to answer. But suppose that someone had asked the sort of opposite question, and by that I mean this question. What is the probability of getting a blue ball on the first, given that we got a blue ball on the second? Now, just reading that question and trying to make your mind think about it makes my mind spin. I mean, I can't even think about it. It's so confusing. And if we want to write it, how would we write it? Writing it is not too hard to do, but thinking about what it means is hard. So this is how we would write it. So what is the probability of getting blue on the first, given that we got blue on the second? So that, as I said, just no way to figure out how to answer that. Okay? And why is it? Because these are sort of in the wrong order, right? We don't get a blue on the first after getting a blue on the second. So it's very hard to think about it. So this is an example of where we could use Bayes' theorem. Why? because Bayes' theorem allows you, if you have A given B, to reverse it and answer the question B given A. And we already saw how easy it is to answer that in this case. And then we would have to do some extra work, as I said, but maybe it will be a lot easier than trying to do this one. So that's kind of the idea, at least that's the way I think of Bayes' theorem. Now that's not what everybody says about Bayes' theorem, but to me that's the power of Bayes' theorem. Now going back to Google, and this is probably from Wikipedia, there's another expression of this. So here's the expression we saw, but there's another expression which is, this is the same expression again, but here is a second expression of Bayes' theorem. So actually the top is exactly the same as we had. The top is still the same, but the bottom gets rewritten. So instead of probability of B, we can write another expression for the probability of B, and that's what they do here. So it looks kind of awful. But this is read not A, or in the language of sets, that's read A complement. This would be A complement. This would be A complement. So it's not too bad, really. And Bayes' theorem and this sort of second version of it can be proved very simply, very easily, and very quickly. All we need to do is write the definition of conditional probability. This is just the definition of conditional probability. So this is just the definition. And then we can also write the definition of conditional probability where we have reversed B and A. It's still, this is just a definition of this conditional probability. Now for this one, we can just bring this up to here, or actually bring it over to here. So put it right there, and just have an expression for the probability of A intersect B is this times this one, because we put this up here. And so we have another expression for probability of A intersect B, and we just replace this with that alternative expression, which is what? P of B given A times P of A. And so that's what we have here, P of B given A times P of A, and that is Bayes' theorem in one of the versions that we've looked at. And then to show what the bottom is, or to show the alternative version of the bottom, you can read a little bit further to show that. But this is, anyway, this is Bayes' theorem, one version of it, and we've just shown it in just basically two very simple steps. Now, I suggest that you go through this and read some of this in Wikipedia. For example, you could read this. I wouldn't, for our class, I wouldn't read this because we haven't talked about it in this form. And you can read this, and you can read this, and this would be a good example to read. And this would be a nice example to read. And this would be a good example to read, although it might be a little bit philosophically challenging. But anyway, I would suggest you read this as well, and this as well. And then if you want to look at the algebra for the expression of P of B, you can look at that as well. Okay, so to review, if we want to be able to reverse a conditional probability question, Bayes' theorem can come to the rescue. So if we have probability of A given B, we can do it as probability of B given A. And we saw an example here where we would definitely like to do that. We don't want to have to think about this in this order, but thinking about it in this order is no problem. Okay, and the last thing is just a little bit of terminology that's used in Bayes' theorem. So I think most people know what the word prior means. Prior means before. And posterior means after. Let's see if we can find something in a dictionary. So here's posterior. And posterior means positioned at or towards the back, or later in time, anterior. So it basically means after, and it comes from Latin. So these words come up in terms of Bayes' theory, prior, before, and posterior, after. Let's see that. Okay, so here is the kind of more complicated version where the denominator is kind of spelled out, but we could just write a very simple expression. Anyway, we're not concerned with the denominator. We're only concerned with this term, the blue box, and the green box. So we're only concerned with this term here and this term here. And this term here is called the prior probability of A. And this term here is called the posterior probability of A. And the reason they use the word posterior here is because it's after being given B. This is the probability of A given B, so it's after being given B, so they call it the posterior probability of A. It means after something, after B. And this one is not given B, so they call it prior to being given B, so they call this the prior probability of B. So this is called the prior probability, of A. This is called the prior probability of A, and this is called the posterior probability of A. And actually this term also has a name. It's called the likelihood. That is, this term here also has a name. It's called the likelihood, but you don't hear that very often. You'll hear it in mathematics, but these other terms, actually, it's very common in common conversation to hear people talking about your priors and updating your priors. Now, anyway, yeah, so the prior is P of A, before being given B, so it's the prior. And updating your priors means changing it based on being given B. But anyway, that's the posterior probability of A. Okay, so that's the terminology that you'll hear. So here, this is called the posterior, and this is called the prior. This is from our book. This is the notation they were using in the book. But anyway, this part here is called the posterior, and this part here is called the prior. Okay, that's all we're going to do with Bayes' theorem. You can go through the examples in the book to get some interesting applications of it.